So, welcome to session number 4 of module 1, in which we will discuss about stress and strain. We will continue from the previous sessions of stress and strain. And in the last session, we looked at how to do the tensile test and how to obtain mechanical properties from the results of a tensile test. So once we get the properties of the materials, those properties we can use to design different mechanical components for different applications. So by knowing the strength of the material, or particularly yield strength, ultimate strength, fracture strength, Young's modulus, we can use this data to calculate or to design different mechanical components for using different materials. So one more concept which you have to keep in mind while designing using the different properties of the materials what we have obtained from tensile test is the factor of safety. So it is related to the allowable working stress, or you simply call it as a design stress. So factor of safety is nothing but, as the name indicates, when you design any components for the different applications, we don't usually use the maximum capacity or maximum strength of the material. So we try to reduce, or we try to make use of only some portion of the strength of the material while actually designing and manufacturing, and particularly applying that material for particular component, particular applications. So we try to reduce the strength of the material by some amount. So that amount is nothing but factor of safety. So usually it will be more than one, because the factor of safety, it is defined as yield strength by allowable working stress, or we call it as design stress. So this is the property of the material. Yield strength or ultimate strength or 0.2% proof stress is the property of the material. It depends on different materials. So this allowable working stress is the design stress what we consider for designing different mechanical components using that material. So for example, a material has a particular yield strength, but while using that material and for particular application, when I am designing that, I will use only some amount of stress. I will not use the maximum yield, I will not use the yield strength of that material, but I will reduce that yield strength by some amount called factor of safety, and that strength or stress, it is called as allowable working stress or the design stress. So it is usually factor of safety will be more than one, because the design stress or design strength, we consider it lower than the yield strength or the ultimate strength of the material. So factor of safety, in other words, you can see it relates strength and the stress. So strength is related to the capacity of the material, whereas stress is what actual stress or the load you are applying on the material when it is being used for particular applications. So strength indicates maximum capacity of the material, whereas stress indicates the applied load or stress on the applied stress or applied load on the material when it is performing or when it is working or while it is in application. So usually all the materials we design or we manufacture them for different applications. So there the strength of the material is taken, it is reduced by some factor, and we take this as design stress, which will be the actual stress or load which is being applied on the material when it is performing or when it is in application. So in other words, you can say factor of safety as the capacity over the ratio over the demand here. So usually capacity of the material will be more, but while designing we demand only some portion, lesser part of the strength. For example, the strength or capacity of the material is 100 megapascal. Say that the yield strength of the material is say 100 megapascal. While designing, I will consider that the strength of the material is only 80 megapascal. So I am reducing the maximum capacity of the strength 100 megapascal to 80 megapascal. That means I will apply the stress or load so that only 80 megapascal is induced in the material when it is performing, or when it is in working, or when it is in application. So I reduce it by some factor, some amount. So that amount is the factor of safety. So here we have one example here. We have what is called as a rope here, a material or a rod, whatever it is, and it is rated as 30 kilonewton. And when it is holding a 2 kilonewton, so this is 2 kilonewton load here. So actually the strength of this material, or the maximum capacity of this material, is 30 kilonewton, but I am loading it with only 2 kilonewton here. So the factor of safety will become 15. So maximum capacity of the strength of the material is 30 kilonewton. 30 divided by the actual stress or load what you are applying when it is working. So that is 2 kilonewton. So 30 kilonewton by 2 kilonewton, it will become 15 here. The factor of safety will become 15. So very high, factor of safety is very high here in this case. So this rope is 30 kilonewton, it is the capacity is or strength is 30 kilonewton, but while designing or while applying, I will put only 2 kilonewton on that. So factor of safety is 15 now. So I can reduce the factor of safety. I can make use of the strength of the material to the maximum level. So I can increase the load. This 2 kilonewton, I can increase it up to say 20 kilonewton. So when the load applied is 20 kilonewton and the strength of that material is 30 kilonewton, so 30 by 20 it will become. So that factor of safety will become 3 by 2, 1.5. So I am using the factor of safety 1.5 when I use the maximum capacity or the maximum strength of the material when it is working. So this allowable stress or allowable, it is called as allowable working stress. Working stress means the design stress or the actual stress which is being applied on the material when it is working, when it is functioning. So as the name indicates, the purpose of factor of safety is to minimize the risk of the failure of that particular component. So factor of safety, the safety word is coming there. So as the factor of safety is increasing, the safety of the component or the safety of the component in which where it is applied, and it is particularly all the materials are applied for human comfort or what is called as human luxury. So for example, automobile, what is called as shaft or axle, whatever it is, IC engine. So when the factor of safety is very high, that means the chances of failure of that component, for example connecting rod or whatever it is, it will be less. So when the factor of safety, when the failure of the probability of the failure of that component is less, that means the service it provides to human being, the reliability is very high. So basically factor of safety is to minimize the failure of the component of the material when it is performing. So again it is nothing but same thing, the same formula, maximum strength of the material divided by the design stress or working stress. So here we have items or factors which affecting factor of safety here. So we have different models, different factors which affect or which help us to decide the factor of safety. So here is analytical stress model. So we calculate the stresses in the material and then we decide the factor of safety, and again it will decide the geometric dimensions of the part. So by using factor of safety, it is affected by geometric dimensions, and also it is affected by magnitude of loading. So it will decide how much load it can be applied on the component, and also the properties of the material. By knowing this, so all these things will affect the factor of safety. So you have to select the factor of safety based on these factors here. So coming to one more concept called as Poisson's ratio. So in the previous sessions we have seen about strain. So strain, and that is you are taken only in the one direction, linear direction. So I told you that whenever load is applied on the component or on the bar here, so you can see here when I apply tensile load on this bar, so you can see here this is dotted diagram is there, that is the initial component here, initial dimensions of the component. When you apply the load, it will stretch, the bar will elongate. At the same time, the lateral dimensions, it is dimension along y axis and z axis will reduce here. Or if it is cross section is circular, diameter will reduce. If the cross section is rectangular, the width and thickness will reduce, but length will increase when you apply tensile load. So here the strain will be in the x direction. Also it will be in the lateral directions, that is in y direction and z direction. So that concept of strain in all the directions, that is y and z directions, is taken here to define the Poisson's ratio. So here we have what is called as, so here this you can define Poisson's ratio in simple terms here. So we have Poisson's ratio nu here. It is a strain, so it is a lateral strain divided by linear strain. So if you go back here, so if the strain is taken in along x-axis, it is the linear strain. So what strain you have understood in the previous sessions, it is a linear strain. So strain or change in dimensions will occur in the lateral directions also, that is along the cross section. So along x-axis and along y-axis and z-axis. So that strain is also calculated, and we get the Poisson's ratio as lateral strain by the linear strain or axial strain. So axial means the strain occurring along the axis of the strain, or we simply call this as linear strain. Linear means along the axis. Lateral means perpendicular to the axis. So the strain which is perpendicular to the axis, that is in y direction and z direction, that is taken there, and that is calculated. So lateral strain means strain in y direction. Axial or linear strain means strain in x direction. Also again, lateral strain you can take in z direction also, divided by linear strain in x direction. So that ratio of lateral strain by axial strain is called as Poisson's ratio. The term is here, and we use the symbol nu for Poisson's ratio. So with these concepts, we will actually go to the how to apply these concepts, or how to apply the different properties to solve different problems, or to design the materials for different applications. And also we can find out the amount of stress and strain induced in the material when different loads are applied, and different kinds of loads are applied. So we have one simple problem here, wherein we have a cross-sectional, rectangular cross-sectional bar here. So we have a rectangular rod or a bar with dimensions 20 mm by 30 mm, and length of the bar is given 500 mm. So you can just imagine this kind of bar here. So this is the bar. So length is given, width and thickness is given. So the cross section of this bar is rectangle here. You can assume circular cross section also. So different shapes you can assume, for it depends on your design which cross section you select. But anyway, in this problem we can assume this kind of bar with rectangular cross section. So the dimensions are given here, 20 by 30, and length is 500 mm, and it is subjected to axial load, and the axial load is compressive. So the axial load can be tensile or compressive. So in this problem it is compressive load of 60 kN. So when you come back to this diagram, so here the load is tensile load, axial tensile load, but in the problem it is given as axial compressive load. So the load will be towards the bar or towards the component, towards the compressive load. And the Young's modulus is given here. It is given as 102 GPa, and this is the Poisson's ratio. Just now we looked at it, The Poisson ratio is given here 0.34. So from this given data, given geometries and material properties, so E and V nu are the material properties, and 20, 30, 500 mm are the geometry of the material of the bar, and this is the load, is the external load what you are applying, mechanical load you are applying on the particular component. When the load is applied, what will happen to the material we will see when we solve the problem. So we told that when the load is applied, there will be stress and strain induced in the material. So how much stress and how much strain, that you have to calculate by knowing these values. So here we have to find out the changes in length. So when you apply compressed load, length will decrease obviously, and also the sides, that is lateral dimensions, also will increase. So how much, by how much amount, how to quantify them, we'll see now. So the bar is subjected to compression, so obviously there will be decrease in length, and the cross section will increase, so increase in depth and breadth will be there. So write on all the data, given data here, and the important thing is you have to calculate the area of that cross section. So the cross section here is the rectangle, so the area of rectangle will be the breadth and thickness. So you can use this. If the cross section is area, if the cross section is a circle, then area will be pi by 4 d square. So it depends on the cross section, whether it is rectangular, triangular, square or circular. So based on that, we calculate the area of that cross section. Then once you know the area and the load is given, so you can directly calculate the compressive stress or stress. So stress is nothing but load by area. So load is compressive load P 60, and area is again just now we calculated that. So it's the area on which the load is acting. So that is stress. So just put the values and get the answer. So you'll get 100 Newton per millimeter square or 100 megapascal, because the load is in Newton, 60 Newton. So kilonewton is there, you take it in 60 Newtons here. So it is 60,000 Newtons, and area is in millimeter square, and because B and D are in millimeters, so you will get area in millimeter square. So Newton per millimeter square is the unit for stress. Coming to strain now, so strain is axial strain, longitudinal strain or linear strain or axial strain. So since the Young's modulus is given, so we know that Young's modulus is applied only in the elastic region where stress is proportional to strain. So directly we can calculate the linear strain or longitudinal strain or the axial strain. So sigma by E. So stress just now we calculated here. Young's modulus is given, you will get the strain, and it is unitless as we were discussed in the previous sessions. And coming to lateral strain, so lateral strain is related to the Poisson's ratio. So here Poisson's ratio is also given. It is given here. If it is not given, then we have to calculate the lateral strain or the reduction in cross-sectional area. So directly you can go with the Poisson's ratio. So Poisson's ratio into linear strain will give the lateral strain. So directly we will get that. And decrease in length. So when you apply compressive load, length will be decreased. So you can go to the strain formula. So what is strain? Strain, that is epsilon L. Linear strain is nothing but change in length by the original length. So if you want the change in length, that is the decrease in length, is nothing but strain into length. So strain just now we calculated here into length. Similarly, if you want strain or the change in dimension in along breadth, that is, so breadth is increasing here. So change in breadth is nothing but lateral strain by breadth, original breadth. So lateral strain just now we calculated here. So you just put the values here. Similarly, the depth also increases, the thickness also increases because you are applying compressive load. So how much it increases, that is the change in depth is nothing but lateral strain into the original length, or lateral strain is nothing but change in lateral dimension divided by the original dimension. So So accordingly you can take the particular dimensions, original dimensions, and you can get the change in length in x-axis, y-axis and z-axis. So you can take this as length in x-axis, this you can take it as y-axis, this you can take it as z-axis. So any changes in dimensions in directions, that will be equal to lateral strain into dimension in that axis. So here directly you can calculate a rod. You can take a rod and you can calculate, when you apply tensile load, you can calculate how much it elongates or what is the extension of the bar or the rod. So elongation or extension or strain, all are same here. So that you can calculate directly. We have small derivation here to calculate what is the change in length of the rod, or what is the elongation of the rod, or what is the extension of the rod, or simply what is the strain in the rod. So here we have a rod here, and you can see it is a length is L, the cross section is circular, and we are applying tensile load here. It is uniaxial, that is we are applying load along the axis in one direction, that is uniaxial. So it's a uniaxial load here. It's a tensile load basically. So when you apply tensile load, obviously the length of this rod will increase by so much, delta. So this is the change in length or increase in length. So what is strain? Strain is change in length by L. So it has changed by delta. So delta by L is the strain. So we also know this formula here. Young's modulus is stress by strain, or stress is equal to Young's modulus into epsilon strain. So this will be P by A record one. So this is the stress is P by A. Stress is nothing but load by area. Young's modulus, keep it as it is. Then you write the formula for strain. So strain is nothing but change in length, that is delta, by the original length L. So now this is the elongation. So change in length is nothing but elongation or extension. So I want this. So rearrange the equation here, terms here. We will get the elongation or change in length delta PL by AE. So you can just remember this formula and directly you can calculate delta instead of using all this rearranging these equations. So directly you can remember this equation. It's a small derivation. So change in length is related to strain. Strain is related to stress with Young's modulus. So rearrange the equations, you will get delta change in length as PL by AE. Just remember this equation. It will be useful while solving the problem. So coming to the problem here, we have one component here, which is circular cross section. So we just imagine a shaft, and you can see the shaft is not straight. I mean, it's not having same diameter throughout the length. So we have three portions in the shaft here in the circular bar. So it's a bar basically. So here we have a length of 250 mm, and the diameter here is 20 mm diameter. And at this portion, that is B, we have the length as 100 mm, and it is square here. So the cross section is square here. Just imagine. So imagine a bar with three portions, A, B, C, and in A, length is different, diameter is different, cross section is different here. So it's circular cross section. And in B, it's square. So the cross section is square here, length is 100 mm. And coming to portion C, this part, so it's a diameter, so it's a circular cross section, length is 400 mm. And this bar as a whole is subjected to tensile load. So this is a given problem. So what you have to find out? You have to find out the stress in each portion or in each cross section of the bar. So in each portion or cross section of the bar, that is ABC, we have to find out the stress. And the load is applied is 20 kN tensile. and this cross section is square. You can see this square 30 by 30, length is 100 mm. So this is circular cross section, A and C are circular cross section, and the diameter is given there. And the material of this bar is Young's modulus is given 210 GPa. So this is the given data, and you have to find out the stress in each portion of the bar. So when they ask to find the stress, first you directly invoke the stress equation. So what is stress? It is force by area. So the load is 20 kilonewton, and coming to area. So area, we have different cross sections here. So it will not be uniform at all the portions of the rod here or the bar here. So what we do is we divide this bar, single bar, into three portions, A, B and C. So now we consider only portion A. So consider only portion A. On this portion A, what is the load here? 20 kilonewton tensile. What is the cross section? It is a circular cross section, diameter is 20 mm, length is 250 mm. So this much is enough for us to calculate the stress. So coming to this here, bar A, that is portion A, what is the area of this? So diameter is given here, so it's circular cross section. So area of a circle will be pi by 4 d square. So d is 20 mm diameter here. So substitute that, you will get the area in millimeter square. So what is the stress in the bar? Stress is nothing but sigma A. Sigma is stress, A is nothing but this portion of the bar. So sigma A, stress in the bar A, is load. So load is 20 kilonewton, 20,000 Newton, divided by area. Area just now you have seen here. Substitute that, you will get that in Newton per millimeter square, or it is megapascal. Similarly, calculate area of the bar B. So bar B portion, this is the cross section is square. So area of square is, you know, it is the side into side. So 30 by 30. So it is 30 by 30, and the formula for stress remains same. So stress in bar B is sigma B. So it is a load by area. Similarly, come to bar C or portion C of the bar. So this portion is again it is a circular cross section because diameter is given. So area of that will be pi by 4 d square. Diameter is 15. So directly you can get the stress in this portion. So like that we can calculate different. So since the cross sections are different, so there will be different stresses will be induced in different parts of the bar when you apply this load. So you can see here, when the load is applied, because the cross section area is varying, the stress also varies in these portions, because stress is equal to force by area. So when the area changes, the stress also changes. But load is same here in this portion, in all the portions. So stress is related to, stress depends upon the cross-sectional area. And here the cross-section is changing, so the stress also changes. And also we can calculate, when you apply tensile load on this, we can calculate how much it elongates, or what is the change in length of this total bar, of this single bar. So here when you apply tensile load, obviously it will elongate, it will extend. So you can calculate the extension or elongation of the bar. So just now you have seen that it is nothing but PL by AE. Just now we have seen that it is elongation, a change in length is PL by AE. So P by A is nothing but stress. So the same formula I am writing here. Extension or elongation is equal to sigma L by E or PL by AE. So P by A is nothing but stress, sigma by LE. And E is the material property. So the bar is made up of only that single material. So E will be remaining same. So now we will calculate the extension of the bar with respect to three portions. So if you want to know the extension of this total bar, single bar, you have to calculate the extension of this bar, extension of this bar, and extension of this bar, and then we will add up. So that will give you the total extension of the bar. So first we will calculate the extension in this bar A. So first we will calculate the elongation in this bar A. So what is the elongation formula? It is PL by AE. It is PL by AE. So PA by A is nothing but stress. So the stress in that bar, we have seen stress in this bar A is known. So it is 63 megapascal. So coming to this equation, stress into L by E. Length of that portion A of the bar is 250 mm. Young's modulus is 210 GPa. Substitute that and you will get the extension or the change in length of bar A or this part of the bar. Similarly, you take extension of the bar B separately now. So in bar B, your length is 100 mm. The cross sectional area already you have found out, that is stress in the bar B you have found out here. Stress is already you know. So stress into length by Young's modulus. So length is 100 mm, stress you have found out here, and E, Young's modulus is same. So you will get this value. So it is extended by 0.01 mm. Part A, section A as portion A as extended by 0.7 mm. Similarly, you take extension of the portion C of the bar. So C portion C of the bar is same formula, sigma L by E. So sigma of this bar you have calculated here 113. Length of this portion C, length of the portion C is 400 mm. So that is L, that is 400 mm, and Young's modulus is same. Substitute that. So the portion C extends or elongates by 0.2 mm. So you can see that bar, in that bar portion A as extended by 0.7, portion B as extended by 0.01, portion C as extended by 0.2. So if you add all these things, we will get the total extension of the bar. So the bar is 1, but we have divided that into 3 portions because the cross section is varying, length is varying. So in each portion you calculate the extension using this formula, and then you add all the extensions, that will give the total extension of the bar. So it is 0.3 millimeters. So in the same problem, if the load is compressive, so here it is tensile. If the load is compressive, then what will happen? All the dimensions will decrease. So it is not elongation here. We don't call it as elongation. We call this as shortening of the bar. So shortening of the bar, if you apply compressive load, it is called as shortening of the bar. The formula remains same. So shortening of the bar is equal to stress L by E. So here it will be, we take this as negative because the length decreases. If it is the tensile load, the length increases, it is positive here. To differentiate that compression and tensile, we give this shortening with negative number, negative value, and extension with positive value. So if the extension is positive, it is tensile load or extending. Shortening means the length is decreasing because of the compressive load. So the length will be decreasing. So when you apply compressive load, each portion will compress and the length of the portions will decrease. So if we add all the shortenings, then it will decrease by so much. So length of that bar will be decreased by 0.3. So we call it as shortening, total shortening of the bar. If the load is tensile, we call this as extension, but formula remains same here. And if the load is compressive, we call this as shortening of the bar. So you can use the same formula for elongation as well as for shortening if it is tensile load or compressive load. So if this is tensile load, we call it as elongation. If it is compressive load, we call this as shortening. Okay, that's it for this session. I will continue with some more concepts in the next session. Thank you.